Our seminar today is by Dr. Belhaiza. He will be talking about the equilibrium models in energy market. Our speaker, Dr. Slim, is an associate professor of mathematics in our department. His research interests are mainly focused on the design algorithms for transportation and energy problems. So please, you have 45 minutes.
Thank you very much, Professor. So, Assalamu alaikum, everyone. Graduate students, fellow beloved colleagues. This is not going to be complicated. Very, it's more oriented towards just simple understanding of some models. Okay? Let's do. So this is the outline of the presentation today. I'll go through an oil production game as a duopoly game. We have some insights.
You are still playing?
Yes.
You're being recorded.
I will post it on YouTube and I'll send the link to the chat. And the second game is a natural gas transportation game. And we have also some insights. And finally, I will just summarize. Okay? So, so first of all, I'll talk about the oil production as a duopoly game. Okay? So we have two main oil producing countries here. We try to determine the best response production, Q1 and Q2. Okay? The market's price is a function of the quantities produced. And each country aims at maximizing its own profit, which is something very, very reasonable. So at the end of the day, for every country I, it has to consider the two variables QI and QJ and maximize its own profits, the total income by selling its oil minus the production of this quantity. So we are assuming a very, very simplistic relation between the price on the market and the quantities on the market, which is just a linear relation, P as A minus B times Q1 plus Q2, which is a very basic assumption. And we are also assuming that the production cost is also linear in terms of the quantities produced. Here we didn't include any fixed cost. Of course, there are, of course, a lot of infrastructure before starting to produce, but we just CR times QI for every country. So this setting of parameters is just to display some values at the end. Huh? So we set A equals 40, B equals 1, C1 equals C2, very basic, very simple assumption equals 10, just to give you numbers, and I know people like that. So that's the main purpose. And of course, the goal of this game is to determine the equilibrium market price. Equilibrium market price. So in the first model, where should I point? Okay. First model is the Cournot model. So I'm going to say his name in French. He was a Nobel Frenchman, secretary of a higher Nobel.
The name is not pronounced.
So I'm not pronouncing it. It's Antoine Augustin de Cournot. Okay. Yes, he lived in the 19th century. Okay, very famous for his theory of the Cournot concept. He proposed, in fact, a duopoly equilibrium model in strategic form. Here, so if you apply the model, the two countries would determine their best responses, Q1 and Q2, simultaneously. Okay, so we have pi 1 of Q1 and Q2, which writes as the income for country 1, so the price that you see, times the quantity produced minus the cost, C1, Q1. And the profit for country 2, which is the price times Q2 minus the cost of production. So, of course, now from this concept, every country tries to just looking at its own profit. Okay? So the equilibrium market price, it's called P star, is obtained using first order and second order derivatives, and I believe any Math 101 student can do this. So we'll have the first derivative of pi 1 with respect to q1. We will find something like this of pi 2 with respect to q2. So we then just solve the linear equation system, first order conditions, and we find these beautiful solutions, I mean parametric solutions in terms of A, B, C. So these are the solutions. So in the case, you have, in this case, for the setting of our parameters, we have here Q1 star equals to Q star 10. And the equilibrium price, if you just plug these Q stars into the linear relation, you got this Q star 20. Okay? So that's an equilibrium. Nobody, what is the concept of? Nobody has any incentive to deviate. Okay? That's an equilibrium. So, of course, and you can also check that the resulting profit for pi 1, pi 2 are 100. And of course, we have to keep this in mind as references because we are compare with other models. Okay? So one of the things which is negative about this model is that Cournot assumes that the agents make their decisions at the same time. Is that realistic? That's the question. So to answer this, that's a German guy. Oh, and the volume that means novelty, yeah, novelty. So high class people. Okay, so because lower class people are not assumed, did not have access to science before this. So Heinrich Freire von Stackelberg, 1934, proposed a duopoly equilibrium model in extensive form. So now they're not decided at the same time, and we're going to give a weight who's the main player. The two countries determine the best response as quantity production as usual, Q1 and Q2, but sequentially. So one after the other. So in our assumption, country 1 takes the role of the leader, and country 2 takes the role of the follower. Okay? So the equilibrium market price is going to be P double star, that's a typo, is obtained using what the concept of backward induction, and I'm going to explain it, and first order and second order derivatives. In fact, backward induction is generally used for extensive form games where we have this sequentiality with games of perfect information. What does it mean? It means that the last player is going to compare its response, its best response in general, to any player, any leader player move. Okay? So that's why it's called backward induction. And so in dynamic programming, we may call it Bellman algorithm. Okay? In some other application, it has a different name. So depending on where you are speaking and to whom you are speaking. So first of all, of course, we're going to use the same thing, and nothing has changed now in the model. Nothing, absolutely nothing. It's just now we start by whom? By the follower. The follower is going to just check what's going to be his optimal or its optimal solution. So we just again differentiate pi 2 with respect to q2, and in this case, you see that Q2 double star is always going to be having this solution, just first order condition. By the way, in the two cases, even in the other case, you can easily check that the second derivative here is negative because you're going to have just minus 2b. So that's a maximum. You want to maximize. Same thing. So now the leader is going to act. So he knows that the follower prepared. That's based on the fact that I don't assume that my opponent is stupid. I assume that if I'm rational, everybody is in this room is also rational. Okay? That's common knowledge. So if he's rational, he's willing to maximize his profit. So I'm going to prepare my best response to his rationality. Okay? So if I know that he's preparing this response, so I'm the leader, I have to act. I'm going to maximize my own profit, taking this into account. So I inject this, I plug this into my PL. Okay? What do I get? I get a different configuration. So pi of Q1 now writes differently. Okay, I injected this into the Q2 double star there, and I finally got this new solution. So you see the pattern of solution. Before, we had Q1 star equals Q2 star. It has exactly the same expression parameters, but now Q1 double star is different, and you see this leader has the highest share of production. And in our setting for our parameters, Q1 double star is 15, just to be 10, and Q2 double star is that's the type of 7.5, 7.5. And the price is 17.5. Now, if you could check, before the total market had 20 units of oil, now it has 22.5. That's it. Sorry for that. Now it has 22.5. Okay, so it increased. But the price, of course, is expected to plunge, to die. Okay, now what about the profit? The resulting profit for each country would be 112.5. And for country 2 is 56.5. Remember that both had 100 units of profit before. Okay? So, some insights. So, for country 1, producing 5 more units of oil, so we can count them in millions, or thousands, or whatever units you want, provided only 12.5 of additional profit. And for country 2, producing just 2.5 less unit, dropped the profit by 43%. Okay, see the sensitivity analysis on the fact or comparing just the two models. So, and for the two countries together, the profit dropped by 31.25. So they're putting more oil, more effort, but less money. Okay, even though they are producing more oil. Okay, so now, is it worth it to act like this? Okay, yeah, we're leaving the position where we were acting simultaneously, but everyone is just maximizing his own, being not altruist, not cooperating, just maximizing our own profit, but simultaneously, compared to a situation where there is a leader and a follower. Okay, is it worth it? What should they do instead? Okay, probably you know the answer. So maybe it is better to join forces and just decide together as a cartel. A cartel has a bad connotation somehow, because it's always linked now to drug and smuggling, but the cartel from economic point of view is just an association of producers or suppliers. Okay?
OPEC is better.
Hold on, yeah.
I mean, instead of cartels, just say OPEC.
No, but it could be, I mean, everywhere. That's the word to be used. So, the OPEC, you heard about it. Are you sure? I'll give you a multiple choice question. Okay. Surely it's not a football team. Okay. So now the OPEC, what does it do? So we have the main producers, and they gather on a table, they meet, okay? And our goal is to please everyone around the table, okay? So around the table here we have two countries. I just sum up some of the problems, okay? Then I will decide afterwards if I have total quantity of oil to put on the market, how I'm gonna share it. Okay? I'm gonna do some basic assumptions. Okay? So by here, which is the sum of the two profits, okay, is the total profit of the cartel. I like the word. Then it writes like this. Just plug it inside, just the sum of the two pies we had before. Just differentiate. With respect now we have two variables, huh? So it's no longer 1 stuff, it's 2 stuff, if you are following with me. And we need to adjust the gradient equal to 0. Right? So and when you want to solve this, you can enjoy, you're gonna have this total quantity in the market, triple star, Q1 plus Q2 is equal to this. Okay, that's the total quantity on the market. So first model, Cournot, we had 20 units on the market. Second, we had 22.5. Third, we had just 15. And if we decide they're gonna just share it equally because we have the same cost, everyone's share is just 7.5, just half. The oil price, 25. And of course, we'll make more money, putting less money. Okay? So the total profit is 225 for all of us, and our shares are equal 112.5. So you see, we have a problem, a situation, and depending on how you're going to set things, you're going to have different solutions. and different outcomes. What do you want? You want just extract oil like Russian, like UK did in the 90s and the 2000s, exhaust all your stocks, sell it at low prices, or wait like Norway did with the oil of the Northern Sea. Then sell it and be able to manipulate the market, play with the price. So the total profit is 225, and the part of the country, each one of them is 125. So of course, the total profit is higher than any other configuration, and producing less, the OPEC ensures that prices remain high and more profit is invested. Right? So that's for our first model. Any question on this before we move to the next?
Isn't the maximum is in a whole line? That's why you cannot start Q1 to Q2. When you solve the gradient.
Yeah, just hold on a second.
That's one doesn't give you what is Q1, what doesn't give you what is Q2.
No, when you solve, you need to. There is only a solution here because the Bell model is simplistic. Only a solution if you set C1 equals C2, because you're going to have this quantity. In fact, Q1 plus Q2 is equal to this from the first condition, plus for the derivative with respect to part of Q1.
You solve two equations and two unknowns. So in case you will have a unique solution, but
but the two unknowns, they could be gathered into just one here, because when you differentiate with respect to Q1, only C1 is left, but this quantity would remain. I mean the sum. Okay, so here in this model, that's one bad thing about this model. It's simplistic. It's just you need C1, C2 to be equal to each other. Okay, and the two other models you didn't need them. Okay. So, any question about this? Any other question? Okay. Fine. Hope you like it. Enjoy it. Okay. So now you know what is a Cournot model. We decide simultaneously. We have continuous intervals for our precision variables. And what else?
The mathematical concept of equilibrium. I haven't seen it.
Yeah, I mean, this is equilibrium from the Cournot point of view. Okay?
But
because the equilibrium concept existed before Nash.
But I believe you will do
Of course, yeah. Be my guest. That's the purpose. So I'm preparing. So I would like to invite you to something else. Any other question, guys? Okay. So from Stackelberg's point of view, there is an equilibrium. From Cournot, there is an equilibrium. From OPEC, there is an equilibrium. Okay? Or cartels. Second example, we have a natural gas transportation problem. Okay? We usually call it either LNG for liquefied natural gas or gas, because you could be handling or transporting the natural gas in different ways. So we have two countries, A and B, and you may try to guess which countries are in my mind. Two countries, A and B, are about to settle a long-term agreement on the supply of natural gas. Why long-term? Because that's not for sure to install pipelines and stuff like this. That's for sure not a short-term. So two possibilities to chop oil. That's a bad thing. I had to show. Should be not a natural gas are on the table. So the first possibility uses LNG tanker, liquefied natural gas tankers. Okay. So these maybe you've seen them somewhere, and very special kind of boats. And the second possibility uses natural gas pipelines. It needs time to be installed. Wars, also conflicts and explosions somehow. Okay. So and here are the conditions of our payoffs. Payoffs, I mean, how much money is going to be to secure up in the long term. So if A and B agree on a long-term natural gas supply contract using LNG tankers, only the payoffs for country A is estimated to 15. So if we agree on what? On tankers. The only mean to sell you is tankers. Okay? So we don't have to invest heavily in pipelines. Okay? So we'll pay 15 for the selling country, 5 for the buying country. If A insists, because we are negotiating, yeah? If A insists on just using LNG tankers, okay, while country B rejects LNG tankers, why they do reject? Because in fact they don't want to pay the cost of installing the pipelines. You have to pay. I mean, pay for the pipelines. I'm not going to pay for the whole. I mean, going through so many countries, doing so many wars, just for your beautiful house. No. Second thing, so we get there some payoff, which is 0 for country A and -10 because 0 why country A because he's not selling at all, and -10 for B because there is a loss of opportunity. For the second, for the third configuration, these are extreme configurations, of course. You will understand in the next table, in the next slide. If A and B agree on a long-term gas supply contract using only pipelines only, the payoff for country A is 20, okay, and the payoff for country B is 10. And intentionally, I made the payoffs on the pipelines to be high. And finally, the last configuration, if A insists on investing on pipelines, so before the other extreme case was insisting on just using tankers alone, with country B deciding not to invest into pipelines, so we get -10 over 1. So the payoffs are summarized in this beautiful matrix. We call it, this is a table with double entries. So the payoffs for A and B are 15, 0, -10, 20, depending on the strategies chosen. And the payoffs for country B are the second item, 5, -10, -10, 10. Okay. Now, we're going to play again. Which configuration is the best? Which configuration is the best? Well, Dr. Rahman. Ready? Yeah. Which one you choose? 2010. You agree? Guys, in the back. Come on. Ladies.
No, ladies are better negotiators.
Yeah, for sure. Ladies, sure.
I don't know, 15.5.
15.5. Okay, beautiful. Any other thing? You said.
Both are
Both are good, huh? That's a good thing. Dr. Wissam knows something. But you may be asked to choose, or you might be asked to choose between these configurations. So I'm going to show you something. So hopefully I can just share this. Stop share. Stop presenting. I'm going to go to the desktop. I'm going to go okay, so that's the software we built. Like how many years I've been here, Doctor? 4 years. 4 years. We built like 15 years ago. Okay, I usually teach it use it to teach. In fact, it was the last part of my PhD thesis, and we're just gonna use it to enter our payoffs. Just show you. You don't need to do. Okay, that's my payoff. Okay, so these are the payoffs. I'm not sure I can enlarge. So these are the payoffs for the country one, 15, 0, -10, 10, and 5, -10, -10, 10. Just to show you before showing you some math, that we can avoid using math now. That's okay. Who teaches math anymore? Not us. So here we're solving the game, and we got 3 equilibria. I'm going to show them. Right? Some of them have been mentioned by people. Okay. Right. Let me go back to the slides. Go ahead. Share it again. So how did we get this? What do you think? Just these slides. think we have to unshare again because you're sharing the software. And Windows, go to Windows. No, the other one. Stop sharing. This one. With that, no. This is that's okay. So next item. I'm going. Oh, Nash equilibrium. That's what Dr. Muhammad was working for. Nash equilibrium. So the solutions to our game here, because of the simultaneous configuration, are called Nash equilibrium. John Nash, 1949, published a one-page paper. One page. In fact, it's less shorter than mine. Okay, was still a Princeton PhD student. Probably you watched the movie, very famous, Beautiful Mind. Russell Crowe played the main role. He got, I think, an Oscar. And John Nash in 1993 got the Nobel Prize, way before. Okay? By the way, in the history of Nobel Prize of Economics, many game theorists have earned it, like mathematicians. John Nash was essentially a mathematician.
In economy, but not in math.
Huh?
In economy.
But they are mathematicians.
Yeah,
They are mathematicians, but in economics. Yeah. So John Nash, he used in fact speaks from point theory to show that there is always at least one equilibrium in any strategic form, possibly in mixed strategies. I'm not going to show you the proof, that's not your business. Who cares about that? So, in fact, in our game, the Nash equilibrium is a solution to what? To these two beautiful linear programs. Linear programs, I mean, it's possible you're teaching it, you know this. So here, for player one, my decision values are x1s. For player two, my decision values are x2s. I plugged here the two matrices, A and B. And the only conditions that I have is that I have two strategies for player one or two strategies for player two. So the x1 entries are two. How much I'm going to allocate to tankers, how much I'm going to allocate to pipelines in terms of percentage. Okay? And the same thing for the country. So the sum of these entries, that's saying that the sum of these variables should be equal. Okay, I'm writing it in linear algebraic form to make it more compact. So here I'm talking about the variables. In fact, these are where x1 and x2 are the two mixed strategies, decision vectors. Mixed strategies, you will understand what I mean. I mean, I'm not obliged to use extreme solutions. Okay, life is not about extremes. It's not white or black. Sometimes mixed colors and different shades of gray are better solutions. And these are the two decision vectors for players 1 and 2. And the dimensions why we have n and m, because in general, we may have different numbers of strategies. Okay? There are famous games that if you want to read more, you can Google. You will have the prisoner dilemma game, the chicken game, so many academic and well-chosen cases. Okay, so here are the so these are the equilibria we have with the software. We could have, in fact, that's a problem I gave to my students for their midterm last semester, 407. Okay. Of course, it's easy to find these two extreme equilibria. The one you said 15.5, that's 1010. That was in the northeast corner, north left corner. Yes, 0101. That's 2010. Okay, and this is a beautiful solution where you have mixed strategies. Okay, so the respective payoffs for every, we do the same thing we did with the previous case, where we have the oil production problem. This is how the payoffs are distributed if we follow the 1010 configuration. So that's the earning of the main country A, country 2, that's 2010, and that's 20/3 for the mixed strategy. Now, you would notice that now I'm introducing also Pareto efficiency. The second equilibrium is Pareto efficient. Why Pareto? What was Pareto? In fact, Wilfredo Pareto, another Nobel guy, Italian poly mathematicians, because he's a civil engineer. His father is civil engineer. Noble also, born in France, moved to Italy, and died in Switzerland. He is the founder of the school of the Swiss school, or Geneva School of Economics. So, Pareto efficiency, what does it mean? We cannot move from it, from this equilibrium, without deteriorating the payoff of at least one of the players. And you see, we have a Nash equilibrium here, but it's not a Pareto efficiency. That is much better. Okay? In our case, using 2010 was the pipelines solution. But the third equilibrium is the only one in mixed strategies. And you may think that it offers a mixture of transportation solutions also, which is that could be less impacted by geopolitical turmoils. Understand? So if my pipeline is being subject to a terrorist attack or something like this, I still can send my gas. Okay? If bad weather, tankers cannot move, bad weather, or there is a blockage at canals of Suez, for example, I still can send gas. Okay?
So you suppose that you have the pipeline as well as the tankers at hand.
At the mixed strategy. Of course, the reality is that the deals are now are either tankers or LNG. Okay? Summary. So we talked about the Cournot versus the Stackelberg game on the oil production case. Of course, what is the main thing? Cooperation is better than conflict. Okay? So if we collaborate here with the OPEC, we got better payoff to share, higher prices, lower production. Yeah. The Nash equilibria are not all Pareto efficient. Okay? That's a misunderstanding. Many people don't understand when they talk about game theory or economics. And mixed strategies also should not be disregarded. They offer alternative solutions in case of more stable solutions. Okay. Thank you very much. Okay.
Questions, please.
Ladies first.
I missed something in the next strategy, in the last example. Why would they stay at this equilibrium while they can get more payoff at the 20?
Yes. Mathematically, how do we get this? Yeah, that's a very good question. Let's assume I'm clear. In fact, that was the fourth question in the exercise in the midterm. Okay? Because they do work analytically, they found this equilibrium, this one. It's very hard to get this one by the Lemke house analysis, because they find just one. And then I give them this. Let's assume that country one is staying. Verify that it's a Nash equilibrium. What does it mean? So, what they're going to do? They take this 473/7, plug it here, because now player 2 is playing. He knows what country 1 is doing, and he's going to try to optimize. I find this 4/9/5. Getting this information back to country 1, okay? I have an equilibrium is if I plug the x2 I get again 4/7, then it's a Nash equilibrium. Which means if this is your response to me, and I have a best choice. This is my best choice. I have no interest to deviate, because give me the signal. That's my best answer to you. I give you my signal. That's your best answer. So that's the Nash equilibrium. In this situation, you have a mixed solution. Even though with 1-0-1-0 also we have the same thing, but we can verify here that's the Nash equilibrium. That's why you got it. In fact, the software gives these extreme Nash equilibrium. Extreme Nash equilibrium, not only Nash equilibrium. I mean vertices, which are the vertices of the polyhedra defining the solutions. Just please.
If you add made these two problems together by summation, for example, addition, these two problems together and solve for over x1 and x2, you will get a Pareto solution, right? But
No,
it's not
solution will not
desirable.
be correct. Because if you are having the two functions, that is another. That will not.
No. Now you want to
I
mix.
mean, add them together. It's not
Okay,
going
okay.
to be-
Now, if you mix these two problems together, so you're maximizing what the sum of the two payoffs.
Yeah.
Okay. Like, of course, you're gonna get just the 2010 solution.
Yes.
Okay. That's the Pareto solution. I have something to say. I know what you want.
Yeah, I mean,
Based on
this
what?
is preferable, but why not the other one?
Huh? Because you maximize the sum of the total profit. The total profit. So the total profit here is 2010, which is 30, much higher than the 20, for sure. You want the highest profits earned by both of the countries. That's the 30. No way this one is going to appear, or the third one is going to appear. Got it? Okay. Now, my question to you is based on what you're giving the players the same weight. Okay, so we don't have the same. Right?
But even if they have different weights, you will have a different.
Yeah, you have a Pareto efficiency based on the frontier based on the calibration you want.
The solution will be a mixed strategy because the weights are not the same.
No, I don't think it's going to be this.
But further, another.
I'm not sure.
Here you are solving the two problems. You can solve the one problem, maximize this over minimize of that.
You mean
Directional?
bi-level programming? Yes, that's one approach. That's one approach also, which leads to the enumeration of all one of the solutions. In fact, one of the first, algorithm design goes on bi-level programming or biometrics. Okay, we can also do more if you want. We can write the primal optimality conditions, okay, and then the dual optimality condition. Put them all together, analyze these complementarity conditions using some binary values, and solve every just one program. I get all of them, all the extreme points. Any objective. That's what I did in my master's. Like, any other question, guys? No complicated questions. These guys are.
Is there any situation where there is no equilibrium? This is the first question. خلاص أنا فهمت. And in the setting of non-convex, if you have your function, which is utility function, is strictly concave, etc. Theoretically, we can find equilibrium. But if I have a situation when I would like to deduce that there is an equilibrium, I can see theoretically what are the utility functions, and I decide whether there is an equilibrium. This is right. Well, you have to do an implementation algorithm.
I'm not sure I understand 100%. Usually, when you build a model, maybe the fundamental thing about the question is the design of the model.
Yes.
Okay? Like, believe me.
And I think in most of the cases you are in the convex setting.
Yeah. Believe me, it takes time to build a model, which is what you can share with your students and make it also subject to an exam. That takes time. Also, the calibration of parameters. What are the conditions on the ABCs? For example, in the first case, give you a solution where all the quantities are integers and positive and stuff like this.
Nice.
Okay. But always, the conditions that the price is linear, and you have a linear condition. For example, a linear relation between cost and quantities produced. At the max, you're gonna have what? Quadratic relation, okay, with negative signs, and you want to maximize, so for sure the second derivatives are negative. Okay. So for sure you're going to have a solution. Got it? That's about designing the model, design and is there always now? We could be in trouble if your parameters are not well set. You can have, for example, here in this case. If we assume that C1 and C2, the solution set is empty. You can check with this case, the solution set is empty because you need Q1 plus Q2 to be equal to A minus C1 at the same time A minus C2, so to show C1 should be C2. So that's you need to work it out, how to get around this. Okay? Now, on a higher level, your question is, do we have always a solution in any strategy from yes. Possibly even in mixed strategies. For example, for some games in strategy form like this one, you could have no pure strategy in Nash equilibrium. No extreme solutions, 1, 0, 0, 1, stuff like this. The only solution is just a mixed strategy solution. We have such a case. Okay? At least, what does he say? Nash? What did he say? What did he say? Possibly in mixed strategies. At least one, possibly in mixed strategies. Like it or not, that's the result of the case.
So instead of have a point, you have just a probability to choose a series of points with good weights.
That's your understanding, correct?
Instead of having one point, you have, in fact, a convex combination of Dirac radius. That's
Right.
this is the mixed.
I'll show you something, okay?
What I understand.
Because I have someone in this room who taught the graph theory last semester. What is my okay. Usually, for example, you see the 1, 0, 1, 0, and in two situations, and 0, 1, 0, 1. Put them as a graph, consider them as nodes, okay? And you see that the 4 over 7, for example, 3 over 7, versus, I think it was 4 over 9, 5 over 9, is something which is between the point that lies between. Something that lies between.
You are convexifying.
In fact, there is the interchangeability. You can see that some node equilibria are interchangeable, some are not. And we know the graph of interchangeability. And we have what we call maximum Nash subset, which is the highest, the subgraph with the highest number of nodes. That's one thing.
For a non-convex set, is there always a?
You cannot answer this. I'm pretty sure if you can find a case.
You are regarding the non-convex set, that is different. Non-convex function, that is different.
I don't get your question.
Yeah, إذا كان
Set or function.
utility function.
Yes, you can solve.
Yeah, well, even if it is not just strongly okay, you can get an equilibrium. I'm asking about theoretically.
There are,
we can prove that there is
there are other concepts that is pseudo, quasi-convex, if they are not convex.
Yes.
But here in this lecture, we learn one point, no life without compromise. You will compromise in each and every stage. Either you are in job, you are in home, or you are in study. Because here we do the compromise. That satisfies